Let me start with a question. Have you ever stretched a rubber band and felt the tension increase the more you pull it? Now imagine instead of a rubber band, you're moving a small positive charge closer and closer to another charge. You're working against an invisible force, the electrostatic force. That work you do gets stored. And we call that stored work per unit charge electrostatic potential. When the source is a single point charge, the potential around it depends on two things: how strong the charge is and how far away you are. The equation is simple yet powerful. V equals 1 divided by 4 pi epsilon naught multiplied by Q over R, where Q is the charge and R is the distance from the point. Now remember, potential is a scalar. So we don't worry about direction here. It just tells us how much work is stored at a point because of a charge sitting nearby. Let's now walk through where this formula actually comes from. Imagine a fixed charge Q and you're bringing a unit positive test charge from far, far away, from infinity to a point r units away. You're moving it slowly against the electric field so it doesn't accelerate. You're just doing work. At any point during this journey, the electric field at a distance x from the charge is given by E equals 1 divided by 4 pi epsilon naught multiplied by Q over x squared. Now to find the total work done, we integrate this force from infinity to r. So the work W becomes integral from infinity to r of E dx, which is 1 divided by 4 pi epsilon naught times Q multiplied by the integral of 1 over x squared dx. Solving that gives us W equals 1 divided by 4 pi epsilon naught times Q over R. And since we are bringing a unit charge, the potential V is equal to W. So we arrive at V equals 1 divided by 4 pi epsilon naught times Q over R. This formula is beautifully symmetric and applies to any point in space near a point charge. Now here's something crucial. What does the sign of the potential tell us? If the charge Q is positive and you're bringing a positive test charge closer, you're doing work against repulsion. So the potential is positive. But if Q is negative, the electric field actually pulls the test charge in, so you don't do work, the field helps you. That means the potential is negative. So a negative potential doesn't mean absence of energy, it just means the field is doing the work for you. Also remember, as the distance r increases, the potential decreases. And far away, at infinity, we say potential is 0. That gives us a nice reference to measure from.
Let's spend a moment looking at what the potential looks like as you move farther from a charge. For a positive charge, the graph of V versus R starts high and gently slopes down towards 0. It shows that the closer you are to the charge, the stronger the stored energy. For a negative charge, the graph lies below the axis, starting from a large negative value and rising towards 0 as you move away. Both graphs approach 0 asymptotically, meaning they get close to 0 but never quite touch it, and the steeper the curve, the stronger the electric field in that region. So near the charge, where the slope is sharp, the electric field is intense.
Time for a quick challenge. Let's apply what we've learned. Here's the problem. 2-point charges plus 3 microcoulomb and minus 2 microcoulomb are placed 6 centimeters apart. We want to find the potential at a point that is 2 centimeters away from the plus 3 microcoulomb charge along the line joining the two. Let's break it down. Step 1. Recall the formula. V equals 1 by 4 pi epsilon naught times Q over R. Step 2. Find the distances. The point is 2 centimeters from the plus 3 microcoulomb charge and 4 centimeters from the 2 microcoulomb charge. Step 3. Calculate each potential. From the positive charge, V equals 9 into 10 to the power 9 times 3 into 10 to the power minus 6 divided by 0.02, that gives us 1.35 times 10 to the power 6 volts. From the negative charge, V equals 9 into 10 to the power 9 times negative 2 into 10 to the power minus 6 divided by 0.04, which is minus 0.45 times 10 to the power 6 volts. Final step, add them up. V equals V plus V equals 0.9 times 10 to the power 6 volts, so the total potential at that point is 9 times 10 to the power 5 volts or 900 kilovolts. This tells us how potentials from multiple charges add algebraically, taking signs into account. Let's wrap up everything we've learned about electrostatic potential from a point charge. We started with the idea of potential as stored work, how much effort is needed to bring a charge from infinity to a point in space. Then we derived the equation V equals 1 divided by 4 pi epsilon naught multiplied by Q over R. We saw how the sign of the charge affects the potential. Positive charges create positive potential and negative charges create negative potential. The graphs of potential versus distance helped us visualize energy distribution around charges and gave us insight into the strength of the electric field. And finally, we solved a real numerical example, combining potentials from multiple charges using the scalar nature of potential. I hope this session has helped you see the elegance of how a simple charge affects space around it and how that invisible energy shows up in electric potential. In the next lesson, we'll go deeper into how this potential translates to potential energy and sets the stage for powerful systems like capacitors. Until then, stay curious and keep asking why. That's how all great physics begins.